Hey all, welcome back to another round of physics. And yeah, we're gonna keep moving here. Magnetic braking. Braking. So if you're familiar, and I don't know if you work on your car stuff or your bike brakes, these all work off the same way. But generally, your car, for example, what happens for braking is that inside your wheel, say inside, like beneath your wheel, there's what's called a brake rotor. A brake rotor. Boom, there's a picture. And what happens, it's a disc, and what happens is when you press the brake on your car, there are two brake pads, okay, one on each side of the brake rotor that squeeze together. Okay, and they clasp that rotor. So, what's actually slowing down your car is physical contact, friction between the brake pads and the rotors. And because of that physical contact, you have pieces that undergo thermal wear and mechanical wear. Magnetic braking, by contrast, is pretty cool because it doesn't require physical contact. Okay? So let me give you the example. Let's say for a moment that we have, I don't know, a magnetic field, say a uniform magnetic field, and we'll put it into the page. Usually we choose out of the page. I thought, okay, let's be different and choose into the page. We'll go ahead. Let's say that the x direction is to the right. We'll call y up and we'll call z out of the board. Okay. So there's that. Now, let's say we have this region of uniform magnetic field. I'll outline it in green just so that we see where it is. Okay. And let's say for a moment that we have a wire loop. We'll say that it has some width W. We'll say that it has some height H. Height H. And say you're taking this wire loop and you are pushing it into this region of the magnetic field. Okay. So let's say that you are moving it with a speed of v towards the magnetic field. Okay. Here's a question for you. Okay. What's the force of the magnetic field on the loop? Let's walk through it a little bit. Qualitatively, then we'll work out the math. Okay. So here's the question. Will this red loop experience a change in flux? Survey says, yes. It will go from a region with no magnetic field to a region where there is a magnetic field present. Now, because it experiences a change in flux, there will be an induced current running through the loop, right? That's Faraday's law. A changing magnetic flux generates an induced current. He said EMF, but difference in potential. Well, if a difference in potential in a conductor drives a current. So there's an induced current. But now we can look at the force of the magnetic field on the induced current. Right? Once you have a current in a magnetic field, there should be a force acting on that current. Okay? And that is the force that we're talking about. That's this force that the magnetic field will exert on the loop. So let's go ahead. Let's get an idea here. So first off, as this loop enters the magnetic field, will the flux increase or decrease? It will, yes, you could say, it will increase going into the board, right? So we'll say that the flux increases, and I'll say in the negative z direction, in the negative z hat direction. Okay? So as you push this in, you'll get a larger and larger flux. And I think of it going it's not really right to think of it as pointing, but it's hard for, how I conceptualize it is that I have a increased flux in the negative z direction. That's not proper terminology. That's how Greg thinks about it. Really, how I think about it is that I think of this line growing in the negative z direction. Maybe I should say the total magnetic field going through the loop. So I'm thinking conceptually of summing the entire magnetic field passing through the loop, and so it's getting larger. That's me, though. You have to personalize it with how it works for you. So I think of it as that the flux is increasing, and the total magnetic field passing through the loop is more and more in the negative z direction. Well, that means that my induced magnetic field inside the loop, so in the region of the loop, has to be pointing out. Has to be pointing in the positive z hat direction, right? I have more magnetic field going negative z as the loop enters the field, so I need to induce a field pointing outwards. Well, using my right-hand rule shortcut, if my induced magnetic field is pointing in the positive z direction, then I need to figure out, okay, well, if I grab this left hand, if I'm grabbing this right-hand piece, okay, so I grab the right-hand piece, if I put my thumb going down and I curl my fingers are pointing in the negative z hat direction inside the loop. Okay, that's not right. Okay, so evidently, I have to run the current in this direction. So the induced current, must be running from this perspective counterclockwise. And we can double check. If I grab the top piece and I curl my fingers down until I'm going through the loop, I'm now pointing outwards. And I can go around and do that for every piece. Good so far? Yeah. So I've got the direction of my current. Let me redraw. And I'm just redrawing now just so that I can see the loop actually somewhat in the magnetic field. Okay. Go ahead. How many different segments do you have to worry about? Yeah, hopefully you got it. 4. You have 4 parts, 4 different DLs, if you will. Right? Remember, the magnetic force is given by the current DL cross B, as in boy. So you have 4 different DLs for this rectangular loop. So we have to think about the force for each of these individual wires. Well, let's go ahead. Let's do for this one, this right-hand wire. Hopefully you see, right? Careful. The force on the right-hand section is 0. There is no force. Why is that? This part of the wire is not in the magnetic field. Okay? So if I want the net force, I should write this. I am looking at the sum from 1 to 4 of each of the forces of the magnetic field on the wires. Well, on this right-hand one, that force is 0. How about the left-hand wire? What should I write? Yeah, hopefully you see it. All right, the left-hand wire, okay, I should have something like the current flowing through the wire. Now I've called the magnetic field constant. We've gotten a distance h. So I can integrate, that's h, times the strength of the magnetic field. And, oh, incidentally, I should say, what direction is that force? Yeah, you got it? I, fingers in the direction of I, B is into the board, so I get that my force is pointing in the x hat direction. So we'll go ahead and put x hat here. Okay. We'll mention that DL is perpendicular to B. So the force acting on this part of the wire, I'll call that the magnetic force on the left-hand piece, is pointing in the positive x direction. Well, how about the top piece? What direction is that force pointing? Okay, so you say IB is pointing down. So for the top piece, it's pointing down, and you probably see for the bottom piece, call that top, it's pointing up. Force, magnetic field, bottom. Next question for you. What can you tell me about the magnitude of the magnetic force acting on the top piece as compared to the magnetic force acting on the bottom piece? You see it? They're the same, which means that the magnetic force acting on the top piece will cancel the magnetic force acting on the bottom piece. I should put it this way. If I take those two and add them together, they're 0. They're same magnitude, opposite directions. Now you say, well, how could I get that algebraically, Greg? You say, perfect question. Let us assume for a moment you see that this top piece, only a certain portion of it, let's call it, I don't know, we'll call it L, script L. Only a portion of it is actually in the magnetic field. Okay. So when you do the integration of dl for the top piece, we can only include the segment that's in the magnetic field. Okay. So let's go ahead and I'll write this out for us explicitly. Say the top piece. what we would want to do is we would want to integrate dl, and I'm taking into account already that the magnetic field and dl are perpendicular. Okay? So I'm getting rid of the vector nature. Now here we have two pieces. We have from, if you will, from 0 to L. And then we would technically have something like this. From L to, I'll say W. Right? You'd break up that top wire into two pieces. One, the piece that's inside the magnetic field, and the piece that is outside the magnetic field. Okay. And of course, the one that's outside the magnetic field, there is no magnetic field, so we can get rid of that. And so the force acting on the top part of the wire is the current times the magnitude of the magnetic field times the portion of its length that's actually inside the field, which I called L. So if we were doing the top piece, you'd have something like, I guess, plus I times B times L, and I'll put in here in the negative y hat direction. And then we should include the force acting on the bottom piece, I, B, L, in the positive y hat direction, if we wanted to be complete. Of course, we see again that since those two values are the same, oh goody goody, we can cancel them out. And we end up with something that says the induced current times the length of the, say the height of the loop, times the magnetic field strength in the x hat direction. That is the net force acting on the wire. Okay. Now let me ask you this. Before entering the field, what direction was the wire moving? In the negative x hat direction, right? It was moving to the left. What direction is the force acting on the wire as it enters the magnetic field? To the right. In other words, well, I should ask, when your force is opposite your velocity vector, does your object speed up or slow down? It slows down. Okay? So what you're looking at here is an example of magnetic braking. You can take a loop, or more often it's a single piece of metal. Okay? It's a metal slab. Okay? And as you push it into a magnetic field, it will try to slow down that piece. As you push it into the magnetic field, the induced current will act in such a way as to try to slow down that object, the loop. Pretty cool, huh? Where do you see this? One place you see magnetic braking is on, for example, on roller coasters. Okay. Look right here. Okay. Do you see right here? Let me highlight it. Those are magnets. Those are permanent magnets on the track. Yeah, well, okay, excuse me. They're either electromagnets or permanent magnets. I would assume permanent magnets would be nice because then you don't have to continually power them. Okay? But what you're looking at are magnets, and you see that little gap in between. That's the gap between the poles. And on the roller coaster cart, there's a piece of metal that as the roller coaster comes through that gap, a plate passes through that gap, and that's where you get your changing flux. Well, that changing flux works to slow down the roller coaster cart. Keep in mind, there's no physical touching here, right? It's all in the magnetic field. It's kind of cool. Yeah. Let me give you another example. Cool, right? Yeah, what's going on here? So here's the apparatus, as you can see, and well, let's take a look here. What's going on? This piece right here, is some sort of plastic composite. Okay, so it's just actually it might be wood, some sort of veneered wood. Okay, not metallic at all. Okay, whereas right here, this is aluminum and this one's copper. Okay, now keep in mind, none of these materials are actually magnetic, right? Copper, aluminum, none are. And what you have right here, these little loops, those are actual magnets. Okay? And what you notice in the demonstration, here I'll run it again. Notice which of the three magnets fell the fastest, the one on the wood, the aluminum, or the copper. Yeah, the copper, or excuse me, the fastest, the wood. Okay? You notice you have wood, you have aluminum, you have copper. Okay? And the magnet on the wood fell really quickly, on the aluminum a little slower, and on the copper the slowest. Well, why is that? What's going on here? Okay. Now, in the previous example, we talked about taking a piece of metal and shoving it into a magnetic field. Okay. What's going on here is that we're moving the magnetic field instead, right? We're keeping the material stationary and we're moving the magnetic field. Okay. Let's think about what happens let's think about a piece of this tube. Okay. And I'm only drawing a small piece, but let's think as the magnet drops, let's say that it's the north pole of the magnet, north and south. As the magnet drops, what happens to the flux of the magnetic field through this small segment of the tube? The flux increases, right? Your flux is increasing going downwards, I guess is the best way to say it. That's how I think of it again. Well, what direction, if the magnetic field strength is getting larger, pointing down, then what direction will the induced magnetic field point? Up, right? If it's getting stronger, pointing in the downwards direction, that means the induced field must be pointing upwards. Well, which way should current run in this tube in order to produce an induced field pointing upwards? And that's where our right-hand rule comes into play. Now, this time, point your thumb in the direction of the current. Okay, so I'm pointing mine to the right. I'm pretending that I'm working on the front face again. So the front face, I need the induced current to point up. That means that I point my thumb to the right, and that'll give me my induced field going upwards. So my field must be upwards. That means that my induced current should be flowing on the front face, it's going to the right, and on the back face, it's going to the left. But now let's think about this. I have an induced magnetic field that is pointing upwards. That could be modeled as a bar magnet like this. So what do? I have a bar magnet going downwards and an induced field that is modeled like a bar magnet, where the downwards moving bar magnet's like this, and the induced bar magnet is like this. Are those two magnets going to want to attract or repel? Repel. Okay. Good. And so, as the actual bar magnet starts falling, current runs in the tube and produces an induced magnetic field that slows down, tries to break how fast the actual magnet is falling. Good? Now, the last piece, why does the magnet fall faster on wood as opposed to aluminum as opposed to copper? You probably already see it. Let me ask you this question. In which of these three materials is the induced current going to be the largest? Yeah, you say in copper. The induced current in the copper is going to be larger than the induced current in the aluminum, which is going to be larger than the induced current in the wood. And I say, why? You say the resistivity of copper is less than the resistivity of aluminum, which is less than the resistivity of wood. In other words, copper is a really good conductor. Wood is a really bad conductor. And then we go back and I say, well, let me ask you another question. Okay? As my current, well, excuse me, let me ask you this. For a current carrying loop, a loop of wire carrying a current, is the magnetic field larger for when current is small? Or is the magnetic field larger when current is large? You say, I got this. Of course, the magnetic field in a current carrying loop is larger when I is large. Remember, a magnetic field of a loop, I'll just say, is proportional to the current. So lower resistivity results in a larger current, which will result in a larger induced magnetic field. And if the induced magnetic field is stronger, that means the force between the falling magnet and the induced magnetic field is larger. Well, if the force between those two magnets is larger, then the falling magnet will be, for lack of a better word, the deacceleration of that magnet is larger. It won't fall as quickly. And that explains this racing magnet thing. Why for the wood it falls quickly, whereas the copper it falls the slowest. Very cool, huh? Okay, I think I'll stop there for right now, but keep chewing this stuff over. We'll get into another example. Maybe we haven't talked about the railgun, so maybe I'll talk about the railgun and that kind of thing. So, hey, thanks for your attention. I'll see you next time.